to our exploration of the tutorial. Today we are looking to chapter 7, interfaces, subtypes and matching. The whole concept of object orientation is based on dynamic dispatch. Dynamic dispatch is this idea that you are calling a method but you don't really know what you are calling. And at the beginning, this looked like pure craziness, like you don't know what this function is doing. Why do you want to call it? The secret is into moving your perspective. If you're calling a statically dispatch method, you know what this method is doing in the call side. That is, the person that calls the method have the control on what the method is doing. When you call a dynamically dispatched method, the caller doesn't know what the method is doing, but someone else does. The object is under control on what the method is doing. But the object is just created by a person. So the person that created the object is in control on what that call is doing. That is, with dynamic dispatch, we are not losing control on what our code is doing. We are delegating the control to another part of the code. That is, instead of having the code deciding what to do in the moment where the method is called, the code decides what to do in the moment the receiver was created. In this way, we can make like a delayed if. We have a point in the code where we take a decision, and then later on, this decision will influence our behavior. I would like to imagine the sage of a mountain looking down and say, oh, with object orientation, time is just an illusion. Decisions from the past will influence your future, and decisions in the future will influence your past. Jokes aside, the true power of object orientation comes into place when we learn how to design our code around this power of making decisions in different moments in time. An iconic example of dynamic dispatch and interfaces is the shape interface, where we can have a square, a triangle, and a circle all implementing our shape interface. And we can have a method draw. And the idea is that we can have a list of shapes and call draw on all the elements in our list of shapes. And when we call draw, we don't know specifically what kind of behavior we are invoking. This behavior has been decided when the shape object has been created. This shape object has been created in the past with respect to the moment in time when we call the method draw on that object. But probably it has been created in the future with respect to the moment in time when we wrote the for all that calls draw on all our shapes. So in some sense we get this inverted causality where the future code influences the behavior of the code that we already wrote in the past. As you see from line 5, in 42 we can implement a method from an interface without the need of repeating the type of the method. That is, in this case, we don't need to write void draw mute canvas det. We just write method draw det. In 42, we insist that every method must have exactly one origin point. So either a method is just declaring the class and that's the origin point, or if it is declared in an interface, then there must be exactly one interface where that method is declared first. So in the example that we show here, where we have a card and a gun, and both the card and the gun have a method numDraw, we cannot have a class wrong that implements both card and gun. Because if that was allowed, then the method draw inside of wrong will have originated from both card and gun. And in 42 this is not allowed. We want a single point of origin. And the idea is that in that point of origin, the programmer is conceptually putting the meaning, what this method actually does. We can have diamond inheritance for interface methods. For example, we can have a shape interface, an animal interface, and a noisy interface. And the shape interface can define a draw method. And the noise in the animal interface will implement shape, and so they will inherit this draw method, but it's still the draw method from shape. So our loud cat can be a noisy animal. That is, it can implement both animal and noisy, and it can specify a behavior for all of the three methods. In particular, animal and noisy are delegating the original implementation of draw to shape. That is, we have a single point of origin for all our methods. Shape originates draw, animal originates run, and noisy originates play. In this example, there is no method that originates from loud cat. Our kitty is simply implementing all the methods from the required interfaces. In 42, we can refine the return type of a method implemented from an interface. So, for example, we can have a monster and a big monster, and they can have a spawn minion method, where the monster spawn minion method just return a monster, while the big monster that implements monster can have a spawn minion method that is more powerful and is guaranteed to always return a big monster. From a design perspective, interfaces should just provide the general structure of our type. That is, just provide the signatures for the methods of this type. Recently, in various languages, interfaces started to be mixed with traits so that we could have implemented methods in interfaces. This is not the case in 42, where interfaces are pure specification. All the methods inside of an interface are abstract. This includes class methods. To understand the importance of having abstract class methods in an interface, consider the following example, where we have our shape and our square that implements shape. And our shape is an interface with a class method num number of sides and a class method this new shape of color. And then finally we have an immutable method void draw canvas det. The draw method will clearly draw our shape, but the other two methods are in some sense more interesting. By being class methods, it means that we can call them on a class instance. That is, we can write square dot number of size and we can get 4. This also means that we can write square dot new shape of blue and we can have a new blue square. However, since those methods are abstract in shape, we cannot write shape dot number of sides. A general shape doesn't have a specific number of sides. In line 20, we show an interesting programming pattern where we have a variable of type class shape, and we call it kind of shape, and we initialize it with square. Now we can check that our kind of shape dot number of sides is equal to 4. And we can also use our kind of shape to create a new square. In particular, we could have method parameters that take in input class shapes, and we can store our class shapes objects inside of various kinds of data structures. In this way, it's easy to separate the moment in time where we decide to create a particular kind of shape from the moment in time where we decide to actually create that shape. So we can take a decision about which shape to create without creating the shape, just by storing the specific kind of shape in the right point in our data structure. At a later stage, we will use our class shape to create our actual shape object, and this in turn will propagate our decision chain when a method is called on the created shape object. Let me be clear, there is nothing new about this. This is just a simpler way to encode abstract factory pattern. That is, in turn, a simpler way to do dependency injection. As we will see later in the tutorial, in 42 there are so many different ways to emulate the expressive power of dependency injection, and depending on the specific case at hand, you can choose one or the other. If you still want that from the surface of your API it look like your interface actually has behavior, you can simply follow the static method pattern in 42. For example, here I'm showing a static method intersect that lives naturally inside our shape interface. You see, it's not the method of the shape, so it can be implemented. Technically speaking, it is a class method of the class intersect, but when you call it, you just write shape.intersect of parameters. So it looks a lot like just a method. Interfaces give us a great expressive power to write very flexible code that is in some sense future-proof, because when new implementation of those interfaces come into play, we can have our old code automatically adapt to the new environment, because our future code and our future decisions can be injected in the past. On the other side, this means that the future can come back to the present to hunt us down. What was that? That is, the future could be cooperative and could be your best friend to create a program that can maintain itself automatically. But the future could also be buggy, wrong, adversarial, or simply not really aware of all the details of what happened in the past. That is, there is a balance here. If we use subtyping and dynamic dispatch, we get more expressive power, sometimes more compact code, but less control. On the other side, if we write more classes and less interfaces, and thus we make more statically called methods, we get more predictability. That is, it's easier for a miserable human with a finite-sized brain to actually understand what's going on in a modular sense, because you don't need to know who created the object. You look to the static type of the object, and that type tells you the behavior of the method. So, flexibility, understandability. Flexibility, understandability. Depending on the situation, depending on your experience, depending on the other constraints, you can choose an option. And good luck, because you never know if you have chosen the right one. Because it may look like you are having a happy time now, but maybe in 3 years' time, where you have to maintain your code, you will see if the future was gonna be cooperative or adversarial. But it's the future, so you cannot know it today, and you have to take the decision today. At least this is the case in most other object-oriented languages. In 42, we have a lot of metaprogramming support, and in the rest of the tutorial we will see how this metaprogramming support allows us to change those decisions or to tweak those decisions at a later stage. On the long term, to write easily extendable code, you should rely on dynamic dispatch. However, on the short term, it could be easier and faster to just use matching. Matching is basically a way to hard code in a specific point of the code a restricted form of dynamic dispatch. That is, we can make a dynamic check and execute some code or some other code. Here, in the method example 1, if S1 is a square, we just return S1. Otherwise, we can call S1.bar, a method on shape in this case, and if the result is a square, we call this result Y and we return this Y. Finally, If S1 is a circle but S2 is a square, we can return S2, but we can modify its side to fit the radius of the circle. As you can see, this method returns a square. So from the type system perspective, here S1, that is declared to be a shape in the parameter declaration of the method, is actually seen as a square because we have passed the match in line 2. In line 4, S1 is seen as a circle. That's why we can call the radius method on it. S2 is seen as a square, and so we can call the width side method on it. And if with match cannot have an else. So if you want to just return the result of a specific branch, it's best to use the return keyword. In 42, we can use this nice round parenthesis syntax to extract components from objects. This is not like Python, where you can extract elements from a tuple one at a time, left to right, following the order of the elements in the tuple. In Python, this creates problem because if you get confused on which is the order of the elements in your tuple, you can very easily just swap them around and get the wrong value in the wrong variable. In 42, this syntax extracts the element in a nominal way. x1 colon y1 is going to search for a method without parameters called x and for a method without parameters called y, and is going to call them in order to initialize those variables x1 and y1. A surprisingly useful application of this syntax is to extract a single unit of information from an object. So for example, here we have this list of shapes SS, and we just extract the size and declare a variable called size all in the same shot. This round parenthesis syntax also works to do if matches. So we can have, for example, our SS list of shapes, and we can extract the leftmost element. And if this element is a square, then the condition of our if match in line 4 is successful, and we can return left as a square. Of course, we can apply this on multiple elements at a time. So we can have our list of shapes SS, takes the leftmost and the rightmost element, and if the leftmost is a triangle and the rightmost is a square, then we can return the right one as a square. We can nest this one level down, and for example we can take the leftmost element of our list of shapes and we can check if it's a circle was center, it's a point. Both checks are dynamic. So we first check if the dynamic type of the leftmost element is a circle, and then we extract the center from this circle and we check if it is at least a point. So this is the end for today. As a summary, in 42, interfaces are following exactly the same role that they follow in other languages. That is, it takes a lifetime of intense dedication every day, 10 hours a day, for 10 years in a row, in order to get just a glimpse on how to use them to design good object-oriented. The good news is that this is still so much easier than any other thing in programming.